Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to go and take another look at FMEA. My last video, just about 10 days ago, I was talking about FMEA and I showed you how to fill an FMEA out correctly. Detailed, high fidelity solution. Well, today what we're going to do, I was at the Six Sigma certification event just a few days ago, and this project was presented to me, and when you see it, it's a very simple project. It's a very simple problem. The company is quite small. There's only about 50 people in the company. They make electromechanical assemblies typically, and what you see is a very practical, simple problem that they had, very typical of a 50-person small and medium enterprise in the UK. So it's not the biggest problem in the world, but what they had to do, because they allowed disaster to creep into their process, because they allowed chaos to creep into their process, they then had to spend 5 months correcting the disaster that they'd allowed to be created. And this is a great example of, it's a simple process. But if you treat it like that, if you treat it with carelessness, if you treat any process carelessly, you go at it half-arsed and you don't give it the respect that it deserves, it will cost you fortunes. Now you'll see that this, when we look at this presentation, it's a very simple thing to fix. So what we're going to do is we're going to take a look at the presentation, and then what I'm going to do is I'm going to say, well, what if we'd have done an FMEA? Let's show you what the FMEA would have looked like for this process and how it would have made you sit up and go, no, we need to take this process seriously. It's about to cause some really serious problems in our organisation. So this is an example of why Six Sigma actually should never exist. These 3-month, 4-month projects should never exist in organisations. They only exist because you design disaster in, and when the pain gets big enough and painful enough, you go back and you treat the process with respect. But if you used FMEA, and you used FMEA at the beginning, Six Sigma would never exist. So what this is a video about is how to put people like me out of business. I don't want to keep talking about Six Sigma. I'd love to talk about why FMEA is a brilliant tool. Let's take a look at the presentation. Okay, so here's the presentation. I've changed the name of the company just to give them a little bit of privacy on this. You'll see it's just been presented just a few days ago, and the project took them a few months, 4 or 5 months, I think, in the end to sort out. So let's take a look at this thing. So what's it saying? The process cannot be controlled in relation to machining of some plastic extrusion. And you'll see this is a very simple process. They are just taking a simple plastic extrusion. They're doing 2 simple machining activities at the end of the plastic extrusion. They're not going well and they're creating problems. And it says here, look, it's creating variability with the product quality. And something to point out, the actual plastic extrusion costs about 20 pence. The final product item costs about £100. It is turning up, the problem turns up in the finished item. The problem does not turn up in the 20 pence channel that they should have machined correctly. It only shows up at the end, and when it shows up at the end, they have to throw the whole item away. £100 goes straight in the bin. They then also get inaccurate stock records, so they run out of this simple plastic extrusion because they're using much more of it than they need to. So lots of cost of poor quality going on here that just isn't needed. Now here's 50 days of the reject data. The main graph, the big peaks up here. This is the production quantity. So this is how many they made. The graph we're interested in now is this thing down here, because this is the reject rate. You can see the data on the left hand side, and if I just blow this up, it probably makes it just a little bit easier to see. 18.5% defect rate. So that's what we've got currently, an 18% defect rate, but very variable. So could get a lot worse than 18%. 18% on average. I'm just looking at some of the numbers. There's one here, look, 42%. There's one here, 55%, 28%. Yeah, 28%. So some of these 53%, you know, when you're getting defect rates like that, you just cannot control anything around this process. So with a lot of these solutions, a lot of these chaotic problems, what do I encourage my client to do? Well, I encourage them to go process flow, cause and effect, NCX, SOP, and we want to get the chaos under control. That is what most Six Sigma projects are about, getting chaos under control. Now this is the process. You can see, look, that it's a simple piece of plastic channel. You can probably see it better in this photo here. If I blow the picture up like that, you can see a little bit better. But they're machining a sort of an area here. This flat spot here needs to be machined off. And the other thing they do, they machine a slot, which you can see in this photo here. You see that semicircular slot in the end? And they're doing it by hand. So they have a Dremel in their hands, and they are doing it by hand with skill. Process currently takes 83 seconds, and it's got an 18% defect rate. Then they go and take a look at the input variables to the process. So this is a very standard approach. What are all the inputs to the process? Because inputs control outputs. So now we have a more detailed problem statement that they're talking about. So, you know, no control over machining the process, 18% defect rate, 63-second process, but 20 seconds worth of cleanup time, etc. We've also got health and safety issues with this manual process, so not great. And then of course the objectives, well, simple things like reduce the cycle time by 50%, take the reject rate down to 0. Somewhere it's probably going to say, does it say health and safety? Doesn't mention health and safety, but really should do. But anyway, they're the obvious objectives for this project. And here are the variables that we saw earlier, and because we don't have control here in large swathes of these inputs, when you let inputs like that be all out of control, what do you create? Chaos. You create an unreliable, unpredictable process, commonly known as chaos. And that's what they've allowed to happen, because they treated this simple process carelessly. They didn't come up with a high fidelity solution, detailed, planned, under control, a controlled process, not a chaotic process. We need high fidelity solutions for world-class businesses. So now they start getting into controlling some of the variables, and this first one is calibrating the saw. So this is a calibration process. This is purely about cutting the piece of channel to the right length. So they put a piece in here which is exactly 100 mil, and then they calibrate it to 100 mil. This little yellow box of tricks here, which is on the saw, has a tendency to drift out every day. So every day there is a little problem with it, and if they don't calibrate it, every time they use the saw, they are likely to see error in the cut length of these extrusions. Then they don't fit together properly and they get all sorts of problems. So we've got a calibration routine. Then they need to get control of all this manual Dremel chaos, using skill to try and get round the problem. And basically all they do is they buy something a little bit more industrial, and what do? They jig it. And with a jig you end up with two places on the jig, stage 1 and stage 2, and stage 1 machines the surface, the bottom of the channel, where there's a little cutaway section, and area 2, when you push the channel in there, you will machine the slot in the bottom. So very simple solution. Here it actually is in action. If I blow it up and get a little bit closer, look. One of the reasons why they've put these examples on the top is because people started putting the channel the wrong way around. You can see the channel, the open end of the channel must face towards the right to do the one process. It must face towards the bottom to do the second process, and people were misorientating the piece. That wasn't clear. Now that they have an example, it's much clearer. Anything else to see? Yeah, you can see the two. They've pushed it in the top there, so you can see they pushed it in here first time, and then they're pushing it in the bottom for the second time, and it does the two cycles. So very simple. And by the way, just to point out, they wanted to get, remember, 83 seconds was the original cycle time. 83 seconds. They wanted to cut that in half. They've smashed it, not 75% of it. Now that's a really good example. People talk about quality costing you money. Quality doesn't cost you money. Quality makes you money, because when your process gets reliable and consistent and delivers every time, all the time, you cannot have processes like that are slow and sloppy. Now a process that's on it, doing the job every time, all the time, will be fast, efficient, and they will make you money. Quality makes money. And here's another great example. And then of course these are all maintenance routines that I've put around the saw and the Dremel. What you tend to find is if you don't do maintenance correctly, that is where variation starts. Chaos starts from maintenance. If you allow sloppy maintenance, if you cut across maintenance routines, chaos will just enter your process in huge quantities and money will pour down the drain. Maintenance is super important. So they've got things about maintaining the saw blade, keeping the cutting fluid, etc. up to level, making sure that the air pressure is right. This is all on the saw, by the way. So they've got maintenance routines in place. They've put a jig in place to take all the skill out of the machining processes. And now if we take a look, what's happened? Well, the reject rate effectively has gone to 0. These terrible results up here, which are showing in the first few, in the results that you're seeing here, this was because they got the orientation. So just something had gone wrong. The orientation wasn't obvious, and once they made the orientation obvious, what's happened? The defect rate has gone to 0. Fantastic. Here's what they achieved. They're saying the defect rate is 3.8%, but quite honestly, looking at it now, it's stuck at 0 pretty much. They've achieved what they wanted to achieve. Cycle time reduced by 79%, saved £3,000. By the way, the defects, look, £10,000 per annum. This had been going on for 3 years. This had cost around £30,000. Can you believe that? Because we didn't have a high fidelity solution, we just decided, all we have to do, whenever you hear an engineer say, all they have to do is, if you hear that phrase, all they have to do, that is a red flag. That phrase is going to cost you thousands of pounds. And in this case, that phrase cost this company £30,000 because some engineer went at the process half-arsed and just said, all you have to do is Dremel the end. It's easy. And no, it wasn't. We were relying on skill. It's cost £30,000. The jig cost them a few £100. They could have saved this money if they'd have gone for an FMEA first as last, if they'd have treated this process with respect. So here is where they've got to. You can see now that all of these things have got C's next to them. They have a control in place. They have a low defect rate, high speed process, high quality, low cost. Get it? High quality, low cost. Brilliant. Yeah, so that's exactly what we want. That's what Six Sigma is about. High quality, low cost. Okay, so there's the presentation. It was a simple thing, wasn't it? But it was a simple thing that's cost them £30,000. Now, as I said at the beginning of this video, none of this disaster needed to happen. All they needed to do was to treat the process with respect and get the engineer, and this is what I'm talking about, the engineer does the FMEA, nobody else. You don't have a big team of people spending hours and days wading through paperwork and creating bureaucratic FMEAs. No, this is a document that helps the engineer design a high quality, high fidelity, well controlled process right from day one. So let's take a look at the FMEA document that the engineer should have completed before this process went live. Let's take a look. Okay, now I've pre-filled out the FMEA just for speed of this presentation. But if we go through the boxes, and I'll just maybe indicate them as we talk about them. We'll just sort of colour them in grey. So the first thing to say, look, is we've got the process step over in the column A of the FMEA form. So you can see the first box, look, cut to length. So in this side of the document, we've got the process step in every case, cut to length, using the Dremel to hand machine the recess, using the Dremel to hand machine the 6mm semicircular slot. Now this is the process that was in that presentation. This is the original process, the way that it was intended to go ahead. So this is the engineer thinking, all we've got to do is give him a Dremel and let him get on with it. So we're going to let him design the process just the way he was going to. Okay, look, so let's go, cut to length. What's critical to quality? Now a reminder about the critical to quality. Critical to quality is the input to the process. It's the input to the process. That's really important. So what's critical to quality about cutting the channel to length? Well, that the blade is sharp and that the calibration is of the scale is done. Then we go, so having looked at those two, we just colour those in, and then it says, if we don't have sharpness, what will we get? Well, if blade sharpness. If the blade sharpness goes wrong, failure mode. Now this is, again, how can the input fail? So the input was blade sharpness. How can the input fail? Well, the blade goes beyond its usable condition. That's the failure mode for the input side. This is really important. Inputs and outputs. If you get these mixed up, the FMEA doesn't work properly. It breaks down and it becomes such an unwieldy, invaluable, useless, I suppose is a better phrase, such a useless tool if you get the inputs and the outputs mixed up. So this is really important. Inputs control outputs. Failure mode. How can the input fail? The blade goes beyond its condition. What will happen? The failure effect. Well, now we get heavy burrs and 100% reject rate. I've given that a severity rating of 7. Now, something that's really important at this point, the severity rating, have a clear scale. Now, I don't have a scale here that I'm referring to for why I've picked 7, but you should write down and it should be your language, your definition for your company, so your engineers can easily choose that. But to me, something that results in 100% rework is going to be high on the severity scale. Rework is definitely not allowed ever, and therefore if you're getting it 100% of it, it's going to be in the high scale as far as severity is concerned. Then it says, well, what's the cause? Well, there's no indication of blade life, so nobody's ever said what the blade life is. We have no idea how old the blade is, etc., etc. So no indication of blade life. Then it says occurrence. Now my occurrence is a 1 to 4 scale. Let me show you my occurrence rating that I tend to use. Here is my occurrence rating. So you can see how likely are we to make the mistake? Are we liable to make the mistake once a day, once a week, once a month, once a year? Now you can add to this if you wanted to. So if you want to add more categories, of course, you could go once every 2 years. You could go once every 5 years. You could add maybe, once an hour up here if you really wanted to. If you want to try and make 10 categories, you definitely could. But the reason why I've used this language, the reason for it is to make it easy for you to judge. Don't forget, you're often trying to judge a process that doesn't exist yet. How can you judge how likely you are to make the mistake? You have no evidence of reject rates or anything at this point. So you're asking the question, well, how likely are we? How often would the blade be blunt? And you could be going here. I think I've decided a 3. So I've decided, given how often we use this tool, the blade is going to go blunt once a week. And if there's no rules, we're going to start making this mistake once a week. And it's easy to make that judgment. Whereas if you start to say, is it a 5% defect rate or a 10% defect rate or a 40% defect rate, you have no evidence. But if you say, yeah, we're more likely to make the mistake once a week, we're more than likely to make the mistake once a month, it's really easy to make a good guess, because that's what you're doing here. You're making a good guess. So get your scales so that you can tune into them and there's no arguments, very little argument, clear and unambiguous. The language that you need to use here needs to be clear and unambiguous. So let's go back to the FMEA form. Okay, so no indication of blade life. I've scored it a 3. And then it says, what's the current control? Well, there is no control. What we do is we run to disaster. What I mean by that is we run until we get the problem, and the problem becomes so acute that someone eventually says, I can't use this anymore, please change the blade. You run to disaster. And that to me is a 10. No control whatsoever. And you can see if I work out the risk priority number, 7 times 3 times 10, I get 210. Now for me, the worst I can be with my scoring system is 400. Yeah, 400. So for me, above 200 is going to be something that is clearly actionable. So I'm above 200, the box goes red. Let me show you, by the way, the scoring routine for the chance of seeing the error. So the controls at the end there that I gave it a 10, no chance of seeing the error at all because I haven't got any controls at all. You can see the language that I've used is based on the control you are using. So I've not tried to say, sometimes they say there is there is a 10% chance the problem will go undetected. There's a 20% chance the problem will go undetected. There's a 30%. There's a 40%. I have no idea how you would score those numbers. But if you say, I have a mistake proofing device fitted, you can easily say, oh, I can therefore score it a 1. I have a mistake proofing device fitted, but it's an alarm type. So I'm halfway into making the mistake, then I get an alarm. That would be level 2. I have daily TPM routines, weekly TPM routines, SPC. I might actually swap those two over, looking at it at the moment. I think those two should be the other way around. But you can see that these are clear and unambiguous scores. If you have SPC in place to control the problem, you straight away just give it a 5. There is no argument. So in my case, I've given it a 10 because there was no controls. So the whole thing now, we've gone all the way across, and that's telling me to do something. So I've got to put a control in place to control the sharpness of the blade. So action would have been taken to redesign that process. The scale calibration, what have we got? Well, the scale reads the incorrect length. That's how the input can go wrong. All the channels will be cut to the wrong length. That's an 8. This is getting more painful now. We know that the electronic scale has a daily error built into it. So every day the scale tends to be out slightly. So for some reason the piece of equipment isn't particularly stable. Therefore we're liable to make the mistake daily. So now I'll give it a 4, and we don't have any controls in place. And again, I'm scoring it 320. Now on a scale of 1 to 400, 320 is a big, big problem. So we would be doing something about that. What else have we got? Let's take a look at using the Dremel for the hand machining the recess. What are the variables? Tool condition would be one of them. Skill of the operator is the other one. They're the two inputs. If we don't get the tool condition right, we'll get rough finish. Now I've called this a minor issue, so I've scored it very low because the surface finish isn't that important on machining the recess. So this one, look, because it's got a low severity, etc., has come in at 60. Even though I've got no control, it's a run to disaster type problem. The actual problem that it causes is pretty minor, so it's green. In theory, I'm not going to do anything. So all of that, if we go across there, that's all being dealt with. Then we've got the unskilled operator machining the recess too long. What would happen if they get this wrong? So we've identified that. Well, what it will do, the resin that we put in the product will run out and it ruins the finished product. It multiplies the error by about 10,000%. I'm going to give that an 8. What's the reason? Well, we're using manual skill and control. What's the current controls? Nothing at all. We're using skill. Therefore, 320. It's a disaster waiting to happen. Now, I'm not going to finish the rest of this FMEA off. But if you look at this, it would be telling the engineer, if you allow this poorly controlled, low fidelity solution, low fidelity, you're just going, all we have to do, and we think that's going to produce a good result by saying the words, all we have to do, if you allow this low fidelity solution to go forward, you run the risk of high reject rates, lack of control on the computer in terms of stock accuracy. All kinds of disasters are going to befall you. By the way, those disasters have been going for the last 3 years in this company on this very process. Had they filled out the FMEA, and all I'm asking them to do is to fill out the FMEA personally, use the tool to help the engineer design high fidelity process controls, then the process would have gone right first time. This project never would have existed. Never would have existed And it didn't need to exist, did it? If you look at it, it's such a simple solution, and yet they allowed it to happen. That's why FMEA is so important. Think about a process that's more complicated than this, that you're not doing FMEAs on. The FMEA is a money-making monster because it allows you to go live with a new process right first time. And that's why you should be doing it and not doing Six Sigma projects. Now there's my example, Six Sigma versus FMEA. I know which one I'd sooner do, even though I love Six Sigma. FMEAs are the way forwards, and if you use FMEA, you will definitely make more money. Now if you wish to get more detail on this, you can buy my book, Drink Tea and Read the Paper. If you go to lulu.com, you can get it either as a paperback book or as an electronic download. In there it shows you FMEA and it gives you advice on how to create a scale which is clear and unambiguous, how to fill out each of the boxes, making sure that the inputs and the outputs are in the right box, and just shows you how an engineer should use an FMEA to make more money.